All right, today we're talking about Chapter 3, Section 5, Optimization of Business, Economic, and General Applications. So, as usual, we're just going to snip this and just put it on the front of the notes. Just basically comes down to saying, this stuff that we're about to do today is pretty darn useful. You actually do see it. Well, you probably don't see it, but it's used quite often in the retail world to figure out, what's the best price I should sell this at. How much does the material cost? What's the best price? Just all that good stuff. So, anyways, first one is gonna sound an awful lot like a college algebra problem, but we're gonna apply calculus to it, and well, go from there. So, the hobby farm has 20 feet of fencing to fence off a rectangular area for an electric train in one corner of its display room. Well, I'm tongue-tied here. So, the two sides up against the wall require no fence. What dimensions of the rectangle will maximize the area, and what is the maximum area? Alrighty, so in order to do this, obviously, first things first, you're gonna need to know a couple of formulas, of geometric formulas, and if you're not familiar with the ones we're going to be doing today, you really kind of need to get familiar with them, uh, because you're not going to be able to do these application problems at all if you can't recall or at least know where to look for the formula. But when it comes to a test, you're gonna have to recall. But anyways, so the area, we know area is if it's a what is it? It just says, oh, it's a rectangular fence. Okay, so it's a rectangular fence. We know the area of a rectangle is area is equal to the length times the width. Okay, so we know area is length times the width. We don't really know too much information besides that, though. We do know that this particular fencing, we have 20 feet of fencing to fence off rectangular area. The two sides against the wall require no fence, so what dimension of the rectangle will maximize the area? So we know that together they're going to equal a certain amount, right? And that amount is going to be 20 feet because that's how much the hobby farm has. So I like to put my formulas up here in yellow. Didn't have to go crazy with that W. There we go. All right, so we know that um, my length plus my width is going to be equal to 20 feet. Okay, and then if we solve this for W, we end up with W is equal to 20 minus L. All right, so what good does that do for us? Well, if we go back and we look at our formula, area is equal to length times width. What I'm going to do is I'm going to substitute this width in for W. Okay, so I'm going to substitute the width in for W. So I'm now going to have my area is going to be equal to the length times my width, which is 20 minus L. Okay, so the reason why we did this is because we know that whenever we're trying to solve for a variable, it's a lot easier. Well, not only is it easier, it's impossible to solve if you have two unknowns and you don't know one of them. It's impossible to solve. So you have to know at least one of the unknowns. Well, in this particular case, instead of knowing the unknown W, we just change it to an L, and now we have an equation with just one unknown right here, which is L. Okay. Anyways, moving on, let's go ahead and take maybe I can just put it down here. Take the first derivative. Well, actually, uh, let's just clean it up real fast. We're just gonna get rid of the parentheses. So we're gonna have 20L minus L squared. Right. And if we take the derivative, now let's put this up here. The derivative, so A prime. All right. The derivative of 20L is just 20. And then the derivative of L squared is going to be minus 2L. Okay, so now we have our first derivative, and of course this is the same thing we've done for the past two, at least two sections. What we're going to do is we're going to take this derivative and we're going to equate it to 0. Okay, So we're going to take the derivative and equate it to 0, and we're going to get our critical point. So we do this, so 20 minus 2L, and we're going to set it equal to 0. And then we end up with L is equal to 10. So this is a critical point. L is equal to 10. Alrighty, so that's the only critical point we have because we don't have the endpoints here or anything. And so we have to figure out, is this critical point a minimum or maximum? Well, of course, we know how to do that because, or we know what procedure to do after that is because we take the second derivative. So the second derivative, right, just turns into what? Just a negative 2. Okay. Well, what would be a prime of 10? Well, it doesn't really matter what a prime of anything is because there's no variable here to plug in, right? The second derivative is always going to be negative. So this tells me that this is going to be a local maximum. This tells me that this L in this particular function is going to be a local maximum. Of course, we know that because my second derivative is negative. Okay, and again, this is everything that we've done before. This entire section is. The hard part of this section, like I said, is to be able to recall some of the formulas, or in some instances, kind of think your way through the problem, as well as recall the formulas. But anyways, we know that 10 is going to be a critical point. We know that it's a maximum. Well, if we plug in 10 into our original equation, well, yeah. All right, so if we plug 10 to the original equation that we made, which is this one, okay, so we get 10, and then 20 minus 10 is 10, so 10 times 10 is 100. Okay, so we know that the maximum, the local maximum on our equation here is going to be located at 10, and then again when we plugged it in, 100. So we know that we have at the point 10, 100, we have the local maximum. Right, and this also tells us that this is where we're going to end up with or this tells us how much fencing that we're going to need. All right, this tells us that we need to use 10 feet of fencing on one side and then 10 feet of fencing on the other because that would maximize our area. Okay. Now, I looked over this section, and a lot of the times, I'll admit, a lot of times you don't necessarily need to do the second derivative test to figure out if it's a maximum or minimum, at least in these textbook examples, because in a lot of these, I say a lot, I can't remember. I'm pretty sure every one of these end up having just one, or maybe two, I don't know, at least one critical point, and that's the critical point we need. The second derivative test is only used to figure out, okay, is this a maximum or a minimum? Is this the number that I want to use? But maybe I'm missing something with how this textbook is trying to lay things out. Alrighty, so a strategy for solving maximum and minimum problems. Now this is super duper important. As you know, I'm really not a big fan of just plain old algorithms to solve problems, but this is one where I think you need to go step 1, step 2, step 3, step 4, step 5. You need to do that in your head every single time. And we're going to go over them because it's very important. All right, so step 1, obviously read the problem carefully. And the big one here is make a drawing. Okay, making a drawing helps me tremendously, and I'm pretty sure it helps pretty much anybody else that does this because it just makes it a lot easier to visualize what exactly you're trying to solve. Right. Step 2, we're going to make a list of appropriate variables and constraints. Step 3, we're going to translate the problem to an objective function f. And number 4, we're going to use algebra and substitution. And number 5, we're going to use the procedures in section 3.1 and 3.4, which is our derivative tests, to determine maximum or minimum values. Right. So the big one here is you always need to make a drawing. All right. When I say always need to make a drawing, you always need to make a drawing. Even if it's a simple drawing, make it. And I'll tell you why with this example right here. Okay. And I'm going to cheat a little bit and not make a drawing. I'm just going to snip the drawing because it looks nice. Okay. Alrighty, so we are Example 2 reads, maximize in volume from a sheet of cardboard 8 inches by 11 inches. 8 inches. Squares are cut out of the corner so that the sides can be folded up to make a box. What dimensions yield a box of maximum value? What is the maximum value? Okay, so starting out here, we know that we know that we have our rectangle. All right, it's 8 by 11. All right, but then it says the squares are cut out of the corners. Right, so obviously I put the picture up here, but the thought process is down here. Um, if I'm cutting squares out of the corners, all right, let's put it. I don't like doing dotted lines. We cut out squares here. Right, now it's easier to visualize. Okay, so if I'm cutting these squares out, right, I'm going to fold up the rest of it, and it's going to make a box style top. Okay, so that makes it pretty easy to visualize. It's also something we're going to use when we talk about constraints here in a moment. But it makes it a lot easier to visualize, and then we can actually attack this problem, knowing what exactly is the end goal here. Okay. Alrighty, so starting off, um, we are wanting to find the maximum volume. Okay. Well, what is volume? Well, volume is going to be the volume of a rectangle or square or whatever is going to be the length times the width, right? Of course, that's just like the area of a square, right? But this is three-dimensional, so we also have to multiply it by the height. Okay. So by the way, every one of these formulas that I'm putting down, you need to memorize because they're going to be used, and you're also probably going to be coming across some formulas that you're not familiar with. So you need to commit all those to memory. All right, one moment. All right. All right. So that's my volume. Now looking at my volume is equal to, well, looking at our drawing up here, what is the length? Well, the length is 11 inches. Okay, true, it is 11 inches, but it's also cut short by a value of x right here and a value of x right here. We don't know how long x is, but we know that x is x units long. So our length is going to actually be, it's actually going to be 11 inches minus 2 x's. So that's my length. Right? My width is going to operate in the same way. Right? Again, looking at this, we know that it is 8 inches long, but again, we have 2 cuts out of that 8 inches. We don't know how long they are. We just know they're x units long, and we know that there are 2 of them. So we would say 8 minus 2x. Okay? And then the height of this box, well, we don't really know the height of this box. Okay, so well, I take it back. We do know the height of this box. The height of the box is going to be whatever this x unit is, right? Because whenever we fold up the like this part right here, we make it vertical and fold it up. It's going to be x units long. So this is our equation for the volume of our square. All right, so this is a pretty easy one. We're just going to have to do some quick arithmetic. All right, so here's I'm gonna do this by kind of foiling it. It's gonna be messy at first, and I'm gonna erase it and make it nice and pretty. So we've got all I did here was I just distributed the x into the first two, and now I'm gonna foil. So we've got 88x minus 22x squared minus 16x squared plus 4x cubed. Okay. Alrighty, so if I clean that up, I'll have a 4x cubed. And then we're going to combine the two middle terms here, so it's a negative 38, negative 38x squared, and then plus 88x. Okay. All right, so this is my volume. All right, so now I have to figure out my critical points. Well, how do I figure out my critical points? Well, I'll take the derivative of my, um, move this stuff up here. I'll take the derivative of my volume equation here. So V prime is equal to, we can do this one in our head, 12x squared, it's like minus 76x plus 88. Okay, so this is my the first derivative, and in order to continue from here, we need to set this derivative equal to 0, right? Well, we run into a very unfortunate problem here because this isn't one that I can factor in my head. I don't think you can even factor this to begin with. Okay. So this is this we set the first derivative equal to 0 to figure out what the critical points are. Right. Well, I'm not going to put the quadratic formula and go through the quadratic formula on the screen, but hopefully you should be familiar with the quadratic formula by now. So we're going to use the quadratic formula on this equation to figure out what the x values will be. So I've got all right. So I end up with x is equal to 1.52 and 53 and x is equal to 4.81. Okay, so these are our two critical points, and at this point we have to figure out, okay, so now we have to figure out which, if this is a maximum or a minimum. Okay, so before I actually kind of reveal something big here, let's go ahead and take the second derivative of this function real fast. So what is v double prime of x? Well, we'll just put v double prime. No big deal. We'll have to put x. Takes up room. The second derivative is what? 6x minus 76. Okay. So 6x minus 76. Did I say 6? I meant 24. Dadgum. I don't know where I got 6. So 24. 24x minus 76. Alrighty. So let's go ahead and, just for fun here, let's go ahead and plug in v. What is v of 1.53? All right, so and then we'll figure out what v of 4.81 is. All right, so we've got negative 30. We don't really care about the decimals here. We just care about if they're greater than or less than 0. So we'll just go stop there. And then v of 4.81 is a 39. Okay. Alrighty. So looking at this, I'm actually glad we did we did do this, because I don't think the book did. All right. So v of 1.53 is a negative 39. So this tells me that at 1.53, right, since the derivative is negative there, we know that it's going to be concave down, and therefore we know that that's going to be a relative maximum, right? So then we know this is going to be a relative maximum, right? And then since 39 is greater than 0, well, we know that's going to be a minimum. Okay. So obviously in this particular case, we're wanting to find a maximum volume, so we're wanting this critical point right here. But one little thing could have been skipped here. We could have skipped taking taking the second derivative of this critical point right here. And why is that? Well, what we need to do here is go back to looking at our box. Well, if our box, all right, our cutout lengths are x units long, okay? Well, if those x's were 4, all right, we're 4.8. If our x's were 4.8, well, we have our box that is 8 inches in length, but we're cutting out 4.8 inserts. All right, so hopefully you see where the math breaks down there, right? If I have to cut out two 4.8 inserts, well then that ends up being what, 9.6 inches. But this side is only 8 inches, so realistically, this number can't even be used. So we didn't even have to do this down here. Take the second derivative of that. But anyways, that's how we do that. And of course, it wants to know what the maximum volume is. So what we're going to do is we're going to plug in our value here. All right, our critical point into our volume equation here to figure out what the maximum volume is. So let's go ahead and do that. So my maximum volume is about 60 cubic inches. So where should I put that? I don't know. Let's put it in this little box right here. So max volume is 60.01 inches squared, or cubed, sorry, cubed. All right, because it's a cubic, it's three-dimensional. But anyways, there's that problem. And again, like I said, that's just example 2. Okay, so like I said, these particular problems just boil down to uh, realistically knowing, kind of the real world um, dimensions of things. All right, now example 3. Example 3 is a really good thinker of an example, one where I feel like, without lecture, you might get stuck on some of the numbers here. Okay. But here we're gonna go ahead and snip the can here. This is important. Alrighty, so reading the example, it says Mendoza manufacturers specialize in food storage containers and makes a cylindrical soup can with a volume of 250 cubic centimeters. The cost of material for the two circular ends is 0.008 cents per square centimeter, and the cost of material for the sides is 0.0015 per square centimeter. So what dimensions minimize the cost of material for the soup can? What is the minimum cost? So we need to figure out what exactly we need to make our dimensions based on those prices to minimize the cost of material, right? So obviously if we want to minimize the cost of material, that way we can make more materials, right? So this makes sense. So let's go ahead and begin the thought process here. Okay, so looking at this can looks like it's comprised of obviously 3 pieces. Okay, so we have, we're told this, and again I just snipped this so it's a nice pretty drawing. We're told that we have a can, and of course these cans are going to have radius r. We don't know what the radius is because we're trying to figure out what dimensions we need to make this can. Okay, well, we don't know what the height is. Again, we're trying to figure out what the height is. But here's where a part of the equation might get lost on some of you. Right here, the length of this square. Okay, so why would that length? Why could we not just put L for length there? Okay, now the thing is, we could, but then we're introducing we're introducing another variable, right? And we already have two variables of r and h. And we don't really want a third variable. That obviously that's one issue. We want to reduce our variables as much as we can, right? Um, but here's where the length of this rectangular part, why it's 2 pi r. Well, it's got to go all the way around this circle. Okay. Well, what is the perimeter of a circle? The perimeter of a circle, the formula for it is 2 pi r, and that's why our length to this square cutout is 2 pi r. Like I said, that might get you lost in some of your examples, but hopefully, since we've done it once, you will see another example like this, and hopefully you recall this part of the lecture, anyways. Okay. So, anyways, we're trying to figure out the cost, and so let's just go ahead and call the cost C. Okay, because we're trying to minimize this, so we're just going to say cost C. Okay. Well, the cost is obviously going to be it's going to be the two sides, the cost of these two sides, plus the cost of whatever this is. Okay. But we're told those costs kind of, right? We're told the cost of material for the two circular ends was this price, and the cost for the side was this price, right? Per square centimeter. Well, we need to figure out exactly how much each one of these pieces are. Okay. Well, this should be pretty simple to kind of figure out a little bit, right? We know that we have the two sides and well, I'm saying two sides. Sorry, the end cap circles as well as the whole big side part right here. So we have to figure out what that cost is. And so in order to do that, we need to figure out, well, first of all, we can say that, well, we're going to end up buying two of these end caps, right? Well, two of those end caps there, right, it's just going to be end up costing 2 times what were we told they cost? Well, they cost 0.0008 cents. So we're just going to multiply that by that number. So 0.0008. Okay. All right. But we also have to keep in mind of their area, right? Because we're trying to figure out what dimensions we need to use. So what is the area of that circle? Well, the area of that circle is pi r squared. So we're going to put pi r squared. Okay. So that takes care of the cost as well as the dimensions of these two circles there. Okay, now I have to take care of the middle part. Okay, well the middle part, all right, so the cost is always going to be plus that amount, right? So if we add that amount, well we know that the side cost 0.0015 cents per square centimeter. Well, we know that that's going to the side is going to be 2 times pi times r. Well, what we're going to do is we're going to multiply this particular function, right? It's 2 times pi times r. But then again, and it's kind of like what we did here. We just kind of inserted 2 times this into our area of the circle. So we're also inserting the price of that, which is going to be 0.0015. Okay. Now, obviously, in this particular case, we can go ahead and combine these two to get to 0.003. So let's go ahead and do that. So we're going to end up with 0.003 and then pi rh, right? Because that is the height, right? The dimensions of it. Alrighty, so I guess we can go ahead if we want. We need to clean this up as well. This turns into looking at this right here. 2 times 0.008 is 0.016. So let's go ahead and fix that. And let's move this a little bit closer. There. All right, so now I kind of have my excuse me, I kind of have my cost function. Okay, but there's a problem with this cost function. What's that problem? Well, I have R and I have H. I have two unknowns, and in order to solve this, I need to have just one of these unknowns. Now let's go back and look at example one to kind of prove a point here. When I wanted to find the area here, right, the area was length times width. The problem here was I have a length and I have a width. I have two unknowns. So what I did was I made a substitution. I substituted W is equal to 20 minus L, and I substituted that in for the W in our area function. That way we only have one variable. So we're going to have to do that here as well, but we're going to have to introduce another equation. Okay, it's an equation that is I wouldn't say similar. It's an equation that's needed for this particular problem, but we have to do it so we can substitute out either an R or an H. Okay, and that equation is going to be the volume of our can. Okay, so the volume of a cylinder is pi r squared times the height. Okay, again, another thing that you need to memorize because it's the volume of a cylinder. It's used often. So we're gonna do this, and what we're gonna do is we're gonna solve this for h. Okay, so if we solve this for h, we'll be able to plug it into our h here. Okay, but wait a minute. We now have 1, 2, 3. We're making things more complicated. Not necessarily, because if we look at our problem here, it says that it gives us a volume already. So it gives us a volume of 250 cubic centimeters. So what we can do is take this equation, change it to 250 is equal to pi r squared times h. Now if we solve it for h, we end up with h is equal to 250 divided by pi r squared. Right? And hopefully you see what I'm trying to do here. Now I can take this h, substitute it in for this h, and now my equation has nothing but r's as a variable. So let's go ahead and rewrite that now. Let's move our toolbar up, but out of the way. So now my cost function is going to be, all right, well, the first part stays the same. We don't have an h there, so 0.0016 pi r squared plus 0.003 pi r, and our h now is going to be, let's just go ahead and put it in yellow to really highlight it, 50 pi r squared, just like that. Okay. So now we can begin the process that we're familiar with of taking the derivative and then figuring out critical points. So let's go ahead and start that. Snip this, put on the next page. Okay. Well, the derivative should be pretty easy-ish, right? So if we did c prime, right? We should probably be doing c prime of our variable, but we'll just stay consistent for this lecture for right now. All right, so c prime here, it would be no, let's actually put of r, so we actually know this time. All right, screw consistency. We're going to do it this way. This is more precise, anyways. Okay, so if r is my variable, all right, so all we have to do is take the derivative of it. So this 2 goes out front, and then that 2 goes down to a 1. So we end up with 0.0032, yeah, 32 pi r. And then this one, right? It's not too complicated because look, this r cancels with one of these r's, right? And then all we have to do is take the derivative basically of that, right? So taking the derivative of this, or taking the derivative of the denominator there. All right, keep in mind we're going to take this r and put it in the numerator, so it's going to look like this. Let's see, what can I? Yeah, we'll just do it this way. All right, so I'm gonna write it down here. It's gonna be a little ugly, and I'll erase it. We have 0.003 pi times 250 divided by sorry. Oh no, even the pi's cancel. Oh, that's even better. Okay, that makes it even easier. This pi also cancels. Okay, so yeah, that makes it even easier. Okay, so that makes it 0.003 times 250 all over just 1r, all over 1r. Okay, and then if I want to, I could take this r and put it in the numerator, if you recall, but I have to make that a negative 1, right? So I end up with what is 0.3% of 250? Let's do that. 0.75. So we end up with a plus 0.75, and then that r turns into an r squared. It's also a negative up here. So minus, and then all over a r squared. Because again, if you recall, we go down one, so it goes on for -2, and then goes back down to a denominator for an r squared. Okay, so that makes it. Hopefully, that makes it nice and neat. Ah, man. All right. So unfortunately, though, we're getting close. We're not done yet, though, because we still have to equate this to 0. So let's go ahead and equate this to 0. We have 0.0032 pi r minus 0.75 over r squared, and that is equal to 0. All right, so putting this into the calculator, we have all right, we have okay, so we end up with two imaginary numbers, so we're going to toss those out. So we end up with r is equal to 4.21. Okay. All right, so this is our critical point again, because this is after we've set the first derivative equal to 0. This is our critical point, um, and like I said, in this particular section, let's go back and look at the problem. It's wanting us to figure out what dimensions minimize the cost. Well, I mean, this is obviously going to be a maximum. I'm sorry, a minimum, and that's because the problem is wanting us to minimize it. But we will go ahead and do the song and dance of getting the second derivative. Unfortunately, so let's go ahead and take the second derivative. C double prime of r. Okay. Well, this turns into luckily pretty simple here, 0.0032 pi, and then this turns into it's going to be a plus now, and it's going to be plus, and it turns into 1.5, put the 2 up front, and then over r cubed. Okay. All right, and if we plug in our critical point into our function here, and let's go ahead and mark off a little bit of room here. So we're going to say C double prime of our critical point, which is 4.21, is equal to, well, I mean, we don't have to actually put this down, do we? Because we just care if it's positive or if it's negative. Well, looking at this problem here, it's going to be positive, like the first part is positive, right? I mean, 0.0032 times pi is going to be a positive number. And then 1.5 divided by, 4.21 cubed, right? It's a positive over positive, which is also positive. So this tells me that this is going to be greater than 0, right? And therefore, we're going to have a minimum. And the minimum is at 4.21. Whew. All right, so there is that. Oh, I think it actually wanted the coordinate too, didn't it? Oh, well, no, just say the minimum cost. So our minimum cost, well, no, I guess, yeah, that would be in the cost formula. So, gosh, all right, so let's go ahead and finish this up. Uh, our cost formula, so it's now going to be C of 4.21. All right, well, what is C of 4.21? Um, I we're just going to go ahead and snip that part of the problem because we're at 40 minutes already. C of there it is right here. And let's go ahead and erase what I did have and make this a little bigger. All right, so there's that. And like I said, I mean for these examples, and I'm pretty sure at least for this section in the book, it's not necessarily needed to find the second derivative, but you will need to. So I mean it's not that much harder. All right, so this time, example, I think we have 7 examples, but I'm not going to do the 7th one because it doesn't actually give you all of the information. All right, so in this particular case, so in the first 3 examples, we had geometric problems, equations that you probably have seen before, whether in your college algebra or geometry class, and you need to kind of recall what those formulas are. Right? In this particular case, we're actually given the formula, which is a nice sigh of relief, I'm sure. But we still have to do the derivative tests. Ready? So, reading the problem, it reads, a drug is administered into the bloodstream of a patient. So we're going to let C of t be equal to 25 Te to the negative 0.04 T, represent the concentration, C of t, in nanograms per milliliter of the drug T minutes after it's administered. Okay, so we're told what each one of these variables mean. What is the peak concentration of the drug in the bloodstream, and when does this peak occur? All right, so what we need to do is we need to take our function, C of t, and we need to differentiate it. Okay. C, let's go ahead, well, I'm going to write C of t here. I don't necessarily have to. Yeah, let's just go ahead and just go straight to C prime of t. Okay, so C prime of t. Okay, it's notice how in the problem it's 25. So 25, we can kind of just disregard that. I mean, it's going to be used in there, but yeah, it's not a big deal. All right, we have a t in front of the e raised to some t power, right? So we're going to have to use the product rule, right? The first times the derivative of the second plus the second times the derivative of the first. So we're going to put the 25 out front, okay, because that just goes with it. All right, so 25 and then t, so 25t. First times the derivative of the second, so this is the first, 25t, times the derivative of the second. So what is the derivative of the second? Well, again, it's an e, so all you do is put the derivative of the exponent in front of the e and then keep the e. So what is the derivative of the exponent, which is going to be negative 0.04, and then e to the negative 0.04 times t. Okay, that's first times the derivative of the second, and plus the second times the derivative of the first. Well, the second is uh, e to the negative 0.04 t times the derivative of the first. Well, I forgot to put my 25 in there. Again, the 25 just comes along for the ride. So 25. Right? And then what's the derivative of t? Well, the derivative of t is just 1, so that it can stay like that. All right, and let's go ahead and polish this up a little bit. Okay, so we can say, well, what is 25 times the negative 0.04? Should be negative 1. All right, so we're gonna have a negative t e to the negative 0.04 times t, and then plus. All right, so we didn't really have to polish up too much there. All right. All right, so that was it. All right, now let's go ahead and take this function and set it equal to 0, and we'll figure out our critical point. So we've got negative t times e to the negative 0.04 t plus 25 e to the 0.04. Oh, forgot to put a t there. Okay, and then we equate it to 0. All right, so we can go ahead and factor out an e. Yeah, we can go ahead and factor out an e to the negative 0.04 t, and what remains is a negative t plus 25 is equal to 0. All right, so we can pretty much disregard this, and then negative t plus 25, that gives us t is equal to 25. Okay, that is our critical point. And again, at this particular point, we can say, all right, so I mean, since we only have one critical point, and this particular problem is wanting to find out the peak, or the maximum, right, the maximum concentration, then it occurs at 25 minutes. And again, I mean, you know what? I am just gonna go ahead and snip the second derivative stuff because we're running kind of short on time here. Actually, I'll just snip this whole thing here. Put it on the next page. Okay. And of course, you see that yes, indeed, the value 25 that we got was indeed a maximum. All right, so 5 and 6, I think the actual rest of them deal with business problems, but we're not going to do 7 because, again, I don't know if I said this right, but 7 doesn't seem to give you all the information that you need. So we're going to just do 5 and 6. Alrighty, so 5 and 6, I know that in my college algebra courses, we do deal with revenue. I say the schools. We do deal with revenue and profit and price functions. But the thing is, you probably only did it that one time, and then never thought about it again. Right, but that's okay because the whole idea behind revenue, price, and cost, well, that it should come pretty intuitive to you because it all makes sense, right? So, for example, let's just read this problem. So, Cruising Tunes determines that in order to sell X units of a new car audio receiver, the price per unit in dollars must be P of X equal to 1,000 minus X. Okay, so that's the price. It also determines that the total cost of producing X units is given by our function C of X equal to 3,000 plus 20X. Okay, so we're wanting to find, for A, we need to find the revenue. Okay, well, looking at what's given to us, we don't really have an idea what the revenue is, but we can build a function based on, I dare say it, common sense. All right, so let's go ahead and think about this. So revenue, let's put this as A, I guess. So revenue, we're going to denote it as R of X. Okay, so the revenue is going to be, how much money do we make, right? Never mind the cost or anything like that. Well, how much money can we make, right? So thinking about this, well, we are our Cruising Tunes, all right? We sell car audio receivers, okay? Well, how do I figure out how much money we can make, right? If we just sell car audio receivers, then it's always going to be the amount of car audio receivers that we sell. Okay. Well, if X is the number of units, well, then we're going to sell X number of units, right? And we're going to multiply that by the price, which is 1,000 minus X. Okay, that makes sense, hopefully, right? I mean, if I'm selling car audio receivers at a certain price, I mean, let's just say it's they're $50. Okay, well, my revenue is how much I sell times the $50, right? That makes sense. So this is my revenue function, and of course, if I just distribute this X through, my revenue function is now going to be 1,000 X minus X squared. That's my revenue. Okay. Now, next up, we're going to have our total profit. Okay. So if above was my revenue, Okay, that's how much I make. Okay, but we have to take into consideration the cost of producing them, right? So it just makes sense, and it should make sense to you as well, that our profit function is going to be my revenue, which I have up here, right, minus my cost. So let's move this down a little bit. Right. So let's move my revenue minus my cost, and my cost is told to us here, which is 3,000 plus 20 times x. So minus, and then we're going to put it in parentheses just so we can, you know, not mix up our negative signs. All right, and let's go ahead and fix this up. So we're going to end up with 1,000 x minus x squared, and then minus 3,000, and then minus 20x. All right, and let's go ahead and make this nice and neat and in descending order. So we're going to put a negative x squared here. We have a 1000x minus a 20x, so it's going to be plus 980x, and then the 3000 is all by its lonesome, minus 3000. Okay, so that is my total profit. So now I have my revenue, my profit, I have my cost, and I have my price. Okay. So now we can proceed, and C reads how many units must be made and sold in order to maximize profit. All right, so maximize, well, there's our keyword there. That pretty much tells us at this point, well, we can now begin the process of taking the first derivative and setting it equal to 0. Okay, so here we go. We have our first derivative, and we're going to go ahead and set it equal to 0. And we'll put that equal sign off to the side. No big deal. Actually, yeah, we'll put it off to the side. Okay. So now what we're going to do is we're going to set this equal to 0. Okay. Well, this is another quadratic equation, and it's a quadratic equation that no, I'm sorry, we don't set it equal to 0 just yet. No wonder. Yeah, we have to take the first derivative. All right. So the first derivative here, and we use what? We use p. All right. So the first derivative here is going to be p prime of x. All right, that's going to make it so much easier to factor. I really didn't feel like doing the quadratic formula on that one. Looks like it's going to be a negative 2x and then plus 980. Oh, so much easier. Okay, so negative 2x plus 980. Now we're going to set it equal to 0. So negative 2x plus 980. We set that equal to 0. If we set, so it's like 490. So we're going to have x is equal to 490. Okay, so this is our critical point. And again, I mean, if we're trying to maximize revenue, I mean, this is where the maximum occurs. Okay, but again, we're in, yeah, we're going to take a second derivative of this. This is a pretty easy one to take a second derivative of. So we're going to take the second derivative of this function. So p double prime of x is going to be, it's just a negative 2. Okay, so looking at this, it's a negative number, so we're looking at a parabola that's concave down. So obviously we have the maximum at 490. So this is going to be a maximum. Okay, and I'm pretty sure we also want to find what is the maximum profit. So in order to figure out the maximum profit, well, what we need to do is if x is equal to 490 here, we're just going to plug in 490 into our equation. So into our price equation. All right, so we go back here. Where are we at? All right, no, we're actually wanting profit. We're not wanting to know the price yet. E is the price. Okay, so the profit, we have our profit function right here. So we're going to plug in 490 in for x. Excuse me. So let's go ahead and put that on the next page. So we're going to say P of 490 is going to be equal to, and of course this is P also, so I'm just going to look at that while I put this into the calculator. All right, so Golly. Okay. Well, that's some pretty good profit there. $237,100. Okay. So this is my profit. Again, all I did was plug in my critical point into my original function. Same thing we have been doing. And then now E wants us to find the price, right? So E is what price per unit yields the maximum profit. Well, this is pretty easy. We can do this one in our head. Looking at my price equation, which was given to us, right? It's 4,000. I'm sorry, it's 1,000 minus 490, so it's 510. So E, right, would be I sell I sell these receivers for $510. I maximize profit, just like that. And well, the math I think is pretty interesting. It's that's something nice and real worldy, right? Okay, so last example we're gonna do for today. Actually, we'll put this theorem up. It's another common sense theorem, I think. Hmm. We'll use it for the next problem. All right, so ticket prices. Oh, that's pretty short. All right, so this is going to be another one of those problems, and you're going to have a couple of these. You're going to have a couple of these that are problems that, I didn't go over exactly. Okay, I can't, as an instructor, I cannot go over each and every single possible word problem ever in existence. What I can do is set you up with tools on how to solve these types of word problems. Okay, so yes, you will have word problems that I did not go over. One moment. Don't get frustrated with me because, you know, like I said, I'm giving you tools. The idea is how to solve word problems, and that's just it. That's all I got. But anyways, looking at example 6, by keeping records, a theater determines that a ticket price of $26 at a ticket price of $26, it averages 1,000 people in attendance. So for every drop in price of $1, it gains 50 customers. Each customer spends an average of $4 on concessions. What ticket price should the theater charge in order to maximize total revenue? So again, we're gonna have to kind of just break this down and think. Okay, so my revenue. All right, so I have a movie theater. Right? Yeah, a theater, not necessarily a movie theater, but a theater. Okay, and there appears to be two ways that I make revenue here. Okay, so the way that I make revenue, and we'll just go ahead and use X as a variable. The way that I make revenue is from um, well, I guess it just be from tickets, right? I make revenue from, and I'm just these are just placeholders. I would write tickets, but just placeholders. They're not necessarily variables. I make revenues from tickets plus concessions. Okay, so tickets plus concessions. So I need to figure out an equation for both tickets and concessions that are similar to one another. By similar, I mean I'm using the same variables here. Okay, because I don't want to have three different variables because then I won't be able to solve this problem, right? So my tickets, how do I figure out what my ticket prices are? All right. Well, or how much revenue I get from tickets. Well, it's obviously going to be the number of people that buy the tickets times the ticket price, right? So let's go ahead and write that. So we've got number of people, and again, this is just spitballing ideas. If you just look at these notes by yourself, you're gonna be like, what is this hashtag P? But anyways, number of people, and then it's gonna be times the ticket, and I'm gonna put sub P for prices. Okay, so ticket prices, and then plus my concessions. Well, it's gonna be the same thing. It's gonna be the number of people. Okay, but times, well, this is pretty easy because it says each customer spends an average of $4. So we have that given to us. Okay. So now we have to figure out an equation for the number of people. We need to figure out an equation for ticket prices, and that's really it, right? Because that's all I have right here. It's a number of people, and of course I can use this particular equation twice. Okay, so how can I figure out an equation for the number of people? Okay, well, it says that we it averages 1,000 people in attendance. Okay, so that's a good starting point. If we average 1,000 people in attendance, okay, um, but then it says that for every drop in price of $1, it gains 50 customers. Okay, so here's where we're going to have to kind of tie in both of these together. Okay, so for every 50 people, so for plus 50 people, all right, we're going to put X here, and I'll go back to this here in a moment. Um, and then we also multiply that by, again, the ticket prices, right? So the ticket prices they start off at $26, but then they go down an X amount, okay, which is every single time that we have 50 more people. Okay, so let's think about this logic real quickly, right? So if if we have, if we add 100 more people, right? 100 more people makes that X be a 2, right? Because now instead of having 1,000 people, we now have 1,100, okay? But that means that, the 50 people happened twice. Well, then that also means that we go down $2. Okay, so hopefully that makes sense. Like if we had, 50 people happen 10 times, right? Then we would go down $10. All right, so that's why we had to connect both of those equations together because, well, in this particular example, they are going to be related. All right, well, and then we say plus, and this is pretty easy over on this side because, well, like I said, we can use this number of people, this equation, for that side on the right as well. So we can say 1,000 plus 50x, and then times 4. So we can just we'll put a 4 out here. Okay. All right, so let's go ahead and clean this up a little bit. We're going to put the equal sign way over here because I feel like we're going to have to do some cleaning here. So, well, let's just FOIL the left side here real fast. Okay, I knew it was 26,000, but I just want to make absolutely sure. My brain's kind of turning to mush right now, as is yours probably. And then that's plus 4,000 plus 200x. All right, let's combine like terms and put in descending order. We end up with a negative 50x squared. I've got so 200, 400, 500x, and then 26 and 4,000 is plus 30,000. Okay. Whew. All right, so that is my revenue function now. All right, that is r of x. So let's take this this r of x and take the derivative and finish this problem off. Okay, so this is this. So r prime of x. All right, so luckily these are I like differentiating these. These are so much easier than fractions, right? So it's 1,000x. I'm sorry, not 1,000. I say so much easier. It's 100x plus 500. Okay. All right, and then we're going to equate this to 0. So we've got negative 100x plus 500 is equal to 0. This makes it just pretty easy. This means that x is equal to a positive 5. Okay. So this is only critical value. If we were to go ahead and well, let's just go ahead. It's not hard. Let's go ahead and do that. So we take the second derivative. That's just going to be negative 100. Okay. So since that's a negative number, right, that means that we is just a concave down. So we have the maximum at x equals 5. Okay. So looking at this, if our ticket prices was 26 minus 5, because I'm pretty sure that's what we're wanting to know, right? The maximum or the best ticket price. What ticket price? Yeah, what ticket price should theater charge? Well, we said our ticket price equation was going to be 26 minus x, right here. 26 minus x. That's my ticket price. Well, if my x value is 5, I get my maximum value. I get my maximum profit. So max profit at $21. tickets. Okay. All right, and that, well, let's see. That does conclude today's lecture, but we're going to go ahead and put the section summary up. All right, now we're officially done.